Okay, so simple harmonic motion is something that's pretty easy to understand, especially with the graphs that we've been doing. These have applications to a lot of stuff. Anything that, so for example, what we're talking about right now is if we have a mass attached to a spring. So here's a spring, here's our mass, let's say. And then here's where S equals 0. Okay, and then what happens is we maybe push this mass upward. So you guys know how a spring works, right? And if we push this mass upward and then release it, what's it going to do? It's going to go down fast and that's it? It's going to bounce around, right? So in a perfect world, this would keep oscillating, but I mean, realistically what's going to happen is we compress, we let go, and it kind of goes down, comes up, but then eventually it kind of slows down and it goes back to its, what we call the equilibrium position, its resting point. Does that make sense? Okay, that's something that we call damped harmonic motion, and you're not going to deal with that in this class. We're going to assume that anything that's going to oscillate or anything that vibrates or anything that has a wave for a graph is just going to continue in perfect fashion forever. Okay. So let's see. Besides springs and stuff like that, where else do you see this? Well, let's talk about this first of all. Frequency. Okay. Frequency is defined. Has anyone done this in physics yet?
Yes.
What is the frequency?
Oh, no, wait. We did spring.
You didn't do frequency?
It goes like this forever, right? Or something like that?
Frequency is just 1 over the period. Okay, and the units are cycles per second, otherwise known as hertz. It's the abbreviation. Okay? So to say something has a frequency of 300 would mean that whatever we have has gone through 300 cycles in 1 unit of time. Okay? 300 hertz. Where do you hear that word, hertz? Sound, yes. Radio stations broadcast over certain waves. And if you ever pay attention to like when they're having those little commercial breaks, I don't know, some of them may not do it anymore. They'll say whatever station FM, and then they might even say broadcasted at whatever megahertz or whatever the frequency is for that station. Okay? So that's how we pick up on where to tune in and all that. All related to trig. Now the stuff we're going to do is not so hard. So all you need to know right now is this new term, which is frequency. We already know how to find amplitude, right? We already know how to find period. The only other thing that will be a little new is this term, which is equilibrium point. But I kind of touched on it a little bit already. Equilibrium point is kind of its resting position, which is right here, at S equals 0. Okay? All right, so let's just go through all the details. For the first graph, for the first spring, here's our graph. S equals 6 cosine pi over t over 4. What is the amplitude?
6.
Good. The period is found how? 2 pi over b. But let's see, what is b here?
Pi over 4.
It's pi over 4. It's this whole thing that's in front of the variable. Our variable here is t. Pi over 4 is the b value. Okay, so if we reduce, what is that going to be?
8.
All right. So we got amplitude, period, and frequency would be 1/8. Just 1 over the period. In other words, in 1 second or 1 unit of time, we've only would have completed 1/8 of the entire period. 1/8 of the cycle. Okay? That's what that means. So let's graph. Let's graph a couple of periods because it'll help answer our questions here. Now, we didn't do this yet, but we should also write down our scale, right? You guys remember how to do that? What's a good scale to use for sine and cosine graphs? It depends, doesn't it? You can't just say 1. That would have to have a lot of things going on. Or pi, that would be a specific case, right? There's a general thing that we did to use a good scale. Period over 4. We cut it into 4 pieces because we want our high and low points, right? So what is the period cut into 4 here? 2. Okay? So these are the extra details that we do when we graph. Is there a phase shift for this graph? There is not. There's no adding or subtracting inside of the cosine. So that means we're going to start right on the y-axis somewhere. How does cosine start? So it starts up at 6. And according to the scale, I'm just going to label our scale increasing by 2. So 2, 4, 6, 8, and I'll do a couple of periods. 10, 12, 14, 16. Label, or not label, but draw in all the points. So we start at 6, we go down to 0, down to -6, and back around. So here's our mass bouncing around. Something like that. Okay? Are there any questions at all on how to find any of these details or how to sketch the graph? If you guys can do that, you know how to do everything in this section because the rest is just answering questions. For example, B, at what times is the mass furthest from its equilibrium point? Well, where visually is our equilibrium point? So these are at equilibrium, right?
So it's the furthest at 6.
Where else is it that far? So at 6 and at -6, that's the position, right? But now what are the times there? Because it says at what times, right? So when does it hit 6?
0.
And then when does it hit -6?
4.
Do you guys see the pattern?
So X.
If I list it out, 0, 4, 8, what's the pattern here? Add 4. So how do we write that? Remember we talked about this nice compact notation instead of listing everything? T equals, pick a value, 0 plus, what's the pattern? 4k, where k is any integer. Well, actually, let's clarify. I'm going to put a little positive sign there. This means only positive integers, because if this is an actual physical scenario, this is where we start our experiment, right? And when we let go, time is only going to be 0 or higher, right? So we're not going to have any negative integers like we did previously. Okay. Now, honestly, for this kind of problem, if you just did this, I'm okay with that. 0, 4, 8, etc. I understand that. Okay. At what times is the mass passing through equilibrium? So at time equals what?
2,
Yep.
6.
Same pattern, right? So how else do we write this?
2 plus 4.
Good. And k can be any positive integer. Okay. So now this is going to be, I'm going to tear this off because we're going to need to compare this in a little bit. You guys shouldn't. Take a minute or two, if you could, and now graph this. Okay? In calculus, you'll learn how to take a position graph and find the velocity of the object just from that graph. Okay? Right now, I'm telling you this is what the velocity is going to be for this object that's moving. You're not going to have to know how to find that. But since it's just the normal trig graph, you guys should be able to sketch the graph and answer some questions. So that's what we're going to do. Okay, so take a minute or two, sketch the graph. I would recommend just doing the same thing we did before. Find all the details. Amplitude, period, scale. There's some space on page 7 for you to graph, if you didn't look at it yet. Remember the packet got unformatted somehow? So, if you're wondering how you're supposed to squish everything in that little space, that's how. I guess you could still do it, though. Okay, let me catch up to you. What's the amplitude here? Careful. 1.5 pi. There's a pi out there. And you'll see where that comes from next year. But for our questions, it's not going to make too big of a deal if you missed it. Period is 2 pi over 4, so it's going to be the same period, right? Which means we're going to use the same scale. And yeah, everything's the same. Frequency. I don't think they asked. Did they ask for that? No, they just wanted the graph. Okay. So I'll do the same thing. There's no shift, so I'm going to start at 0 and then go 2, 4, 6, 8, 10, 12, 14, 16. And if the amplitude is 1.5 pi, that means my high and low points, we have 1.5 pi and then negative 1.5 pi. And now I just got to fill in the points. This is a sine graph. Where does sine start? Do I go up or do I go down? Why down? You guys are so good. Okay. Down. So then fill in the points. So something like that. I just want to put these together so you guys can kind of compare, okay? All right, so let's answer the questions. At what times is the velocity equal to 0? So that's pink or blue graph here. Blue is velocity, right? Where? That refers to pink graph because that was position. Let's just keep that straight. So velocity graph, when is it equal to 0? Let's write it down. At time equals what?
0 plus 4k.
0, 4, 8, etc. So in other words, t is 0 plus 4k, where k is any positive integer. And now the important question, where is the mass at these times? So now which graph should I look at? The pink one, specifically at 0, 4, and 8. Well, at 0, 4, and 8, I'm at 6, negative 6, 6, and I just keep bouncing back and forth between 6 and negative 6, right? How can we say that? Where is the mass? Very nice. I like how you said that. So the mass, let's write it down. The mass is farthest away from equilibrium. Does that make sense? Okay. All right, last question. At what times is the velocity, so let's look at the blue graph, a maximum? So where are those values?
6.
All the 6s, right? So at time equals 6, what's the next one? 14. What would the pattern be? Plus 8. So we'd say 6 plus 8k. And then the important question, where is the mass at those times? So let's look at the pink graph. At time equals 6 and 14 and so on, where are we?
0.
Which is called the... Good. So the mass is at equilibrium. Which, if you think about it, I hope makes some sense. If you compress, if we do slow motion and you compress the mass, let's go back to my picture. If you compress the mass upward, right here, and then you let go, when you let go, what velocity does it have?
Wait, that second?
At that exact moment in time when you let go?
0.
0. And then as it starts to move, it starts to gain speed, but as it passes through equilibrium, now it's got to decrease speed, right? Because it's got to go back the other way at some point. Does that make sense? Okay, so that's how everything's tied together. The last thing I wanted to point out is just kind of the... I mean, this is okay if you guys don't do this, but I do want to clarify. This is okay. We should add the value k equals 0 here. Because if we say only positive integers, that would mean k could be 1, 2, or higher, and then we're skipping 2. Does that make sense? Okay, so I'm not going to be too strict about that because I know it's new notation for you guys. But just so you guys understand, and same thing down here. K could also be 0 because we want to include... Sorry, I'm off the screen there. We want to include this value of 6. Okay, but yeah, that's it. Are there any questions on simple harmonic motion? Yes, sir. 0 or positive integers? No. Never. Anything else? Okay.